Okay, let's remember geometric series, the first type of series that we talked about. Okay, a times r to the n. We knew that when r, the absolute value of r was less than 1, then we converged. Okay, if it's greater than or equal to 1, it would diverge. Now, example of this series is like 1 over 3 to the n. This ends up being a geometric series. You can rewrite it as 1/3 to the n. Okay, and if you looked at the terms, and starting from 0, you'd have 1 plus 1/3 plus 1/9 plus 1/27, et cetera, et cetera, et cetera. And you're really just taking the previous term, multiplying it by 1/3 every time. All right? And what you could say is that the next term, a sub n plus 1, divided by the previous term, a sub n, gave you that ratio, 1/3, right? Okay, good. Well, there's a test that kind of goes along this manner and helps show that series converge, and it's called the ratio test. Okay? First, we got to make sure that, you know, we qualify to being possibly converging. We have to make sure a sub n, the limit as n approaches infinity of this approaches 0. Now, if it does, turns out if we look at the ratio of the absolute value of the next term divided by the previous term, as we trend towards infinity, okay, just like that whole geometric series, next term divided by the previous one, if this is less than 1, then we are going to absolutely converge. Okay? It's like the geometric series. It's like if we know that you're multiplying something by the previous term by something less than 1, well, we're going to be decreasing in a manner that will be that when we're adding up all of our terms, we are going to converge. Okay? Now, if this is greater than 1, we know we're going to diverge. Pretty much when it's greater than 1, we'll find that this limit will not equal 0. When it equals 1, we're not going to know. Okay? If I am continuously, if I look out into the future, multiplying my previous term by 1 to get my next term, then I'm not sure. Okay? But this should make sense. All it is like the ratio. What are we multiplying the previous term by to get the next term? If it ends up being less than 1, we're actually good, as long as my terms are trending towards 0. Okay? So we are going to tackle a guy like this. Does this converge? Something like 2 to the n over n factorial. We will use the ratio test to figure out if it converges or not. The other tests, like the integral test, I can't take the antiderivative of that. It's not a P series. It's not a geometric series. It's not an alternating series. We're going to need the ratio test for this type of series. But we have this factorial. And my first question really is, what is this? Is this even equal to 0? I don't know. So let's kind of review factorials a little bit, talk about the growth rates of factorials before we tackle this series and whether or not it converges. Okay, so let's recall factorial. So factorial is just a mathematical process that says we are going to multiply our term by the previous term all the way until we get down to 1. Now, if I have n, how I would write n factorial out is that I start with my value n, multiply it by the previous value, which would be written as n minus 1, multiply by the previous all the way until I get down to, not plus, silly, all the way till I get down to 3, 2, and 1. Okay? Now, if I have n plus 1 factorial, well, I know my first term is n plus 1. But I can just take that n plus 1 and multiply it by n factorial. And I know what n factorial looks like, and I'm good. Right? Because it's just the first term, and then the next term would be n plus 1 minus 1, which is just n. Okay? If I have 2n factorial, how can we write that? Well, it's kind of like you see it. 2n would be my first term, and then 2n minus 1 would be my next term. We would continue to go down until eventually we'd get to n factorial, and we'd have that kind of disappear on us. What if I had 2n plus 1, and I have n plus 1 in parentheses around 2? Well, I'd first start by rewriting this as 2n plus 2 factorial. And now I know I can say, okay, well, that's 2n plus 2 times 2n plus 1 times 2n factorial, which can be written as that. Okay, we need to be able to understand this because we will be using this to help simplify things when we use the ratio test. Okay, so that's the first thing, is writing things out. But now the second thing is like the growth of n factorial. And like, what's going to grow faster, 2 to the n or n factorial? You know what? I'm going to make it even easier to figure out. What grows faster, 10 to the n or n factorial? Well, let's think about some values like 2. Well, 10 squared is definitely bigger than 2 factorial, right? Let's just actually look through a fun program called Wolfram Alpha at some values for n. So if I look at 10 squared, 100, 2 factorial, just 2. Okay, so it looks like 10 squared and 10 to the n is going to be faster growing. Well, let's look at 20, 10 to the 20th power. We got 21 digits here, 10 to the 20th power. And if I look at 20 factorial, you would think, oh, 20 times 19 times 18, it's got to be less than that. 21 digits compared to, oh my goodness, we are at 19 digits already. I started with 100 compared to 2, and I'm already at 21 digits compared to 19 digits. It appears that the factorial is catching up. It's like the Patriots. Well, let's see. Let's go 10 to the 100th, right? It's a huge number, huge number. It's 101 digits. It's that many zeros. I think I need to show more, but we're good. That's a Google, yeah. Well, how does 100 factorial, 100 times 99 times 98, compare to that? It is 158 digits. The Patriots win. They always do. Okay? So what we find is that no matter what value we use, eventually a factorial will win as we trend towards larger and larger values of n. So what grows faster? N factorial. This is actually the second fastest growing function out there. What's the first? What grows faster than n factorial? Well, like a version of n of a factorial, yes, would grow faster. But there is another thing that grows faster. So let's see. Let's compare powers. We had logs. That's the slowest. Grows slower than x to a power, right? It'll grow slower than a number to the power, which will grow slower than a number factorial. Nope. The combination of these two, n to the n, or x to the x, is the fastest growing. Right. But if you think about x to the x is definitely faster. If you think about, 10 to the 10, well, it ends up just being n times n times n times n, however many times, compared to n times n minus 1 times n minus 2. So obviously this one is bigger than that one, right? Okay, so that's important. That's going to tell me that if I see a sum like this, limit, or the sum, n starting from 1 to infinity of n factorial over 5 to the n, I immediately know that the numerator is growing faster than the denominator. This is going to trend towards infinity, which means this diverges. Numbers are the slowest. They don't grow at all. Constants don't grow. Forgot about that. This should be an x up here. Sorry. This should be a number. X to a power, a number to the x power, a number x factorial, not a number factorial. Number factorial is just a constant. I was off there. And then x to the x. That's nice. Okay, so good. So this equals infinity. That diverges. Well, now, we just answered that. We can look at this. This does approach 0. So that means it possibly converges, Mr. Ramos. It doesn't mean it definitely converges when the limit equals 0. It just possibly converges. We need a test to prove that it converges. Okay? So this is where we are going to use the ratio test. The ratio test. We are going to see if the limit as n approaches infinity of the absolute value. Did I use the absolute value earlier? Good. Of the absolute value of a to the n plus 1 over a to the n, what that equals. If it's less than 1, we win. If it's greater than 1, we lose. If it equals to 1, try the integral test, because this isn't going to work. Now, it's important to understand, what does a to the n plus 1 look like? Well, we can write it out. Instead of just using n, we're going to use n plus 1. Now, when we substitute n for n plus 1, it is always good to use parentheses when you're doing it. Sometimes it's necessary, sometimes it's not. The 2 to the n plus 1, it's not necessary to use parentheses, but in the n plus 1 factorial, it's very useful. Okay, so this is going to be the absolute value of 2 to the n plus 1 divided by n plus 1 factorial all over a to the n, which is just this. 2 to the n divided by n factorial. Okay? Now, this is never going to be negative, so I can kind of get rid of my absolute value after this step. Okay? I don't have any, flip-flopping in the signs. It's going to be positive, so absolute value is going to go. Also, don't like to divide this. In the future, we will go kind of straight to this step, where we will write this as a product of reciprocals. Okay, and again, we are finding the limit as n approaches infinity of this. Well, it's going to be nice if I kind of move things to their partner's side. So 2 to the n plus 1, put it over 2. N factorial, put it over n plus 1 factorial. Now, I need to find this limit as n approaches infinity. So really, we're going to look at our highest degree terms, but things are kind of complicated. It might be better if I just simplify this before I look at my highest degree terms. We can kind of figure out what's going to win, but let's just simplify it. So I'm going to rewrite this guy to the n plus 1 as 2 to the n times 2, right? Because it's 2 to the n plus 1, 2 to the n times 2 will give you that same thing, divided by 2 to the n. And here on the right side, I'll have n factorial over. Remember how I can rewrite n plus 1 factorial? It's just an n plus 1 times an n factorial. Well, now all of a sudden, things get a lot easier to deal with. Stuff will disappear on me, and I'll end up just finding the limit as n approaches infinity of 2 over n plus 1. And what do I get there? 0. Is 0 less than 1? Yes. Which means this converges. We already know it's going to absolute converge because it's not going to be negative at all. So it's going to absolutely converge. By the ratio test. Okay. Pretty involved process, but it's what we have to do when we deal with something like this, which can't be compared to a p-series. It can't be compared to a geometric series. Let's look at this guy. Now, I know that 2 to the n does grow faster than n cubed, but the question is, does it grow fast enough faster for this series to converge? Now, I know that the limit as n approaches infinity of this equals 0, which means I possibly converge. We're going to have to go further to show that it definitely converges. Let's use the ratio test for something like this. You guys use the ratio test, and let's see what we can do here. I'm going to show every step along the way if you want to check. Okay, really the last part, the trick is that this limit as n approaches infinity is 1, which is bad, but I have this 1/2 here. That's good. That gives me the 1/2. That value is less than 1. So that means eventually, as I keep adding terms in the series, I'd be adding terms that are half of the previous term. Ends up being just like a geometric series, which will converge that r value is less than 1. Questions about this? Okay. Let's do one like this. And then I'm just going to keep talking even after 350. If you want to stay and listen, that's great. If you need to go, then go and watch the rest of the video online, because we're got to talk about power series. Use parentheses when you plug in n plus 1. It is vitally important. I got rid of the absolute value when I got rid of the negative 1 to the n. Showing the proper steps, doing this carefully. We will do this unit. We actually will do this as well next unit as well. So we're going to continue to practice because it is something that shows up on free response questions. Okay? Okay. Now that we know the ratio test, we're going to talk about just in general a power series. Now, a power series is just a series with a variable in it. Okay, so x to the n over n factorial. If I wrote out what this series is, I would start with 0. I would say this is 1, x to the 0 is 1, n factorial, when n is 0 is 1, plus we'd have x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, going on and on and on. Okay? It actually is a polynomial that we can kind of graph and see, at least parts of it. Okay? And what we're going to do with these are answer questions like we've done already. Go ahead. You're free to go now if you want to go. I'm going to keep talking. So we're going to see if these will converge, these power series. And we've already had some power series, like a power series that ends up being a geometric series. We had an x in here. The question is, find x so that the series converges. And you said, okay, that's easy. We know that just the absolute value of 2x minus 1 over 3 had to be less than 1, being a geometric series. I'd end up multiplying by 3. I'd get absolute value of 2x minus 1 is less than 3, which means 2x minus 1 has to be between 3 and negative 3. And then we solve, getting 2x is less than 4 and greater than negative 2, and x has to be less than 2 and greater than negative 1. So we did problems like that. And we did ones with a p series, where we had n to the p. And we knew that this is going to converge when p, which is 3x minus 1, is greater than 1. Remember, p series, we have to be greater than 1. We have to get 1 over n squared or 1 over n cubed. We don't want 1 over n. We don't want 1 over root n. So I add 1. I get 3x is greater than 2. And then x is greater than 2/3. Fantastic. Well, now we are going to look at guys like this. And we're going to figure out which of these and when do these converge. And it becomes a different type of problem. It's not something we can bake into a geometric series. It's not something we can say is a p series. Instead, we need to use the ratio test. Okay? And the ratio test says this is going to converge when the limit as n approaches infinity of the stuff to the n plus 1 divided by the stuff to the n, which is the same as multiplying by the stuff, the reciprocal of the stuff to the n. And this absolute value, if that is less than 1, it will converge. We can actually go through the whole process using the ratio test, and we can figure out when this works for given x's. And that's when we will be absolutely convergent. So let's see what we have. All right, well, I have it all in terms of a to the n plus 1 divided by a to the n. Let's go ahead and move stuff around. We will get rid of the negative 1s and get rid well, let's just hold on to the absolute value. We'll get rid of the negative 1s in a second. Let's just go from here. So I have x minus 2 to the n plus 1 divided by x minus 2 to the n. I'd have n over n plus 1. And we're also going to have 5 to the n and 5 to the n plus 1. And we have the negative 1 to the n plus 1 and the negative 1 to the n. Absolute value of this has to be less than 1. Okay, well, this can be written as x minus 2 to the n times x minus 2. which will cancel with this x minus 2 to the n. Gone. This I can't do anything with. This is 5 to the n over 5 to the n times 5. The last one I can actually write as negative 1 to the n over negative 1 to the n times negative 1. Okay? Now, these will go away. These will go away. And I will look at the limit as n approaches infinity of this. Well, I end up with this being equal to 1. I need a little bit more space here. All right, so what do we have left? We got a lot of stuff here. And this is what happens when you're doing these problems. We end up with the limits as n approaches infinity. I'm just going to rewrite it so we can see it clearly. Absolute value, we got an x minus 2. We got n over n plus 1. Then we end up with a negative 1/5. Okay? Well, what I can do, and this is a property of absolute values, is I can just pull this negative 1/5, this constant out, and this will become a positive 1/5. The limit as n approaches infinity, and I'll just say, okay, this goes and pulls out to be a positive 1/5. Okay, so it's kind of like just getting rid of that negative, the negative, but it's a little bit more important here. Now, as n approaches infinity, this is going to approach 1. Okay, so that means that for my series to converge, the absolute value of x minus 2 times 1/5 has to be less than 1, or x minus 2 has to be less than 5. And we can set up our situation where we have x minus 2 is between 5 and negative 5. And we say x has to be less than 7 or greater than negative 3. Okay? All right, great. Well, looks like we're good. Looks like we found the x's that would make this converge between negative 3 and 7. Now, what we did along the way was find the radius of convergence. Okay, if you think about this, if ever I plugged in 2 for x, I would just be adding up a bunch of zeros. Okay, this would be kind of what is considered the center of convergence. When I'm adding up zeros. Well, then, from there, we see that we can expand up to 5 from 2. So we go up to 7, and we go down to negative 3. Okay? What we find is that this value here kind of shows me the radius of convergence. So at 2, I'm going to get some zeros. I can go all the way up to 7 and down to negative 3. The distance here is 5. The distance here is 5. So this is what we consider the radius of convergence. The distance from the center, when we're adding up zeros, to the outsides or the endpoints. Okay, so cool. My radius of convergence for this series was 5. But there's something else that is super important, and it comes along from careful examination of the ratio test. Let's go back to the ratio test. The ratio test says that if the absolute value of a to the n, a sub n plus 1 over a sub n is less than 1, the series absolutely converges. Well, what does it mean to absolutely converge? That means we converge if we have an alternating series or if we're just positive, right? But if we conditionally converge, we still converge. So absolute convergence is correct for this. We would converge, this series right here, would converge absolutely between -3 and 7. But could there be a situation where I conditionally converge? What we will find is that every single thing on the inside here, we are going to absolutely converge. We're good. But once we get to the endpoints, we could have a situation where we conditionally converge. So if I were asked about just convergence, I need to test my endpoints. Okay, so let's go ahead and check my endpoints for this guy. We know we are going to absolutely converge between 3 and 7. We're going to check to see if there's a situation where we could possibly conditionally converge. So I'm going to check when x is -3. Now, if x is -3, my sum, I'll do it up here, n approaches 1 to infinity, would be -1 to the n, then -3 minus 2 is -5 to the n, over n times 5 to the n. I can rewrite that as -1 to the n times -1 to the n times 5 to the n. Right? This can be written as -1 times 5. We can distribute the power to be like that. And that's n times 5 to the n. These -1s will multiply each other out and just cancel. It ends up being -1 to the n squared, which will just be positive, it'll just be 1. The 5's to the n's will cancel, and I'll just end up with 1 to the n. We know that this is going to diverge. This is the harmonic series. Let's check the other endpoint. So if I check 7, I have n equals 1 to infinity of -1 to the n times 5 to the n over n times 5 to the n. These will cancel, giving me -1 to the n over n. This is an alternating series. It's the alternating harmonic. This converges. Which means if we want to talk about just overall convergence of this, yes, we absolutely converge between 3 and 7, but we would say we just overall converge, including 7, but not including -3. And that would be my interval of convergence for this series. It's very intense, this process. It involves a lot of practice that is needed, and we are approaching it just like the geometric series problem, just like the P-series problem, but it's a lot more to do it. A lot more to do. So let's do another one, okay? We want to find the radius of convergence and the interval of convergence. We don't want the absolute convergence. We just want the overall convergence. So I'm going to do this one without the -1 to the n. I'll just treat it just like this. And here we go. We know that this is going to approach 0. Well, we don't know if this is going to approach 0. We have to find the x values so that this converges. So I'm going to use the ratio test. Now, a to the n plus 1 would be written as x minus 4 to the, now I'm using parentheses when I plug in n, 2 to the n plus 1, and then this is 3 to the n plus 1. Okay, so I'll have the limit as n approaches infinity of x minus 4 to the 2, absolute value of x minus 4 to the 2 n plus 2 over 3 to the n plus 1 times the reciprocal of this. Okay, I'm dividing by a to the n, so I'm multiplying by the reciprocal here. Okay, and I know this has to be less than 1. Well, let's go ahead and rewrite it. I'd have x minus 4 to the 2n times x minus 4 squared. This would be divided by x minus 4 to the 2n, and that would cancel. Here, I'd have 3 to the n over 3 times 3 to the n. These would cancel. And I know that this limit, as n approaches infinity, has to be less than 1. Okay? Well, all that's left is that x minus 4 has to be, x minus 4 squared, has to be divided by 3, has to be less than 1. Well, I could do the whole process of pulling out that 1/3 and making it a positive. It is a positive, so I don't have to worry about it. But I can pull this out of the absolute value. It becomes positive, remains positive. I can multiply both sides by 3. And I get that the absolute value of x minus 4 squared has to be less than 3. Immediately, I find my radius of convergence. And I know that I'm going to center this radius of convergence around 4. Now, we would have to say x minus 4 squared is less than 3, greater than -3. And we're going to have to check my endpoints once I find it. So I take the square root of both sides. And I'd be between the square root of -3 and root 3. I don't love this, but we're going to have to deal with it. That would be my interval of convergence right there. Okay, this would be the interval of absolute convergence, and we're going to have to check to see if we would converge at the endpoints. So back up to this guy. I will take him and plop him over here. And let's check our endpoints from the other guy. Okay, so first one, root 3 plus 4. I'd have sum, n starts at 0, going to infinity, of root 3 plus 4 minus 4 to the 2n. divided by 3 to the n. This ends up being root 3 to the 2n over 3 to the n. I'm going to rewrite this as root 3 squared to the n over 3 to the n. This is 3. 3 squared is, root 3 squared is just 3. 3 to the n is 3 to the n. So this would end up being 3 to the n over 3 to the n. So, boom, this is 0. This would end up being 1. And when it's 1 and I add up a bunch of 1s, we're definitely going to diverge. So I don't love this. I actually don't love the other one. I actually don't like this problem. So I'm going to do another one. This one was a little bit too complicated. So let's tackle this guy. Let's find the radius of the convergence and the interval of convergence. So I'm going to use the ratio test to find out when this is going to, what values for x this will converge. So here we go. The limit as n approaches infinity of, we'd have the absolute value, -1 to the n plus 1. I'll do just everything all at once, -1 to n. Then the n plus 1 would be in the denominator, and n would be in the numerator. Then I have x plus 3 halves to the n plus 1 in the numerator. And an x plus 3 halves and to the n in a denominator. That's got to be less than 1. What do I end up having? This is -1 to the n times -1. The -1 to the n's cancel. I'll just be left with a -1. This is n over n plus 1. This is x plus 3 halves. And then the x plus 3 halves to the n would cancel. And this would have to be less than 1. I can pull out the -1, make it a positive 1. Don't have to do anything to it. This would approach 1. So I'd end up with the absolute value of x plus 3 halves has to be less than 1, which means x has to be, x plus 3 halves has to be between 1 and -1. Add 3 halves, x has to be between 5 halves and, sorry, I have to subtract 3 halves. So -1/2 and -2 halves minus 5 halves. Okay? It turns out this would be my radius of convergence. This is my interval of absolute convergence. The question is, will we absolutely converge, or is there some location where we can conditionally converge? We will check our endpoints for this one. So we'll start with x equals -1/2. If I plugged in -1/2, what would I get? Sum n starts at 1, goes to infinity of -1 to the n over n. -1/2 would make this 1 to the n. So I'd end up with -1 to the n over n. This just goes away. This converges because it's an alternating series, the alternating harmonic series. Let's check the other one, x equals -5/2. Well, it would turn into the sum as n starts at 1 goes to infinity. I have the -1 to the n over n. -5/2 plus 3 halves would be -1 to the n. -1 to the n times -1 to the n is -1 to the n squared. -1 to the n squared will always be +1. This will end up turning into 1 over n. Well, we'll find while we do these and we test the endpoints that we'll typically get a, alternating series harmonic and a harmonic. One will converge, one will diverge. This is the harmonic series that diverges. So we converge at -1/2. We diverge at -5/2. I would add a negative, an equals to sign right here, and I'd say that we would converge on this interval between -5/2 and -1/2, including -1/2. Okay, absolute converges. We would not have to check the endpoints if we wanted to just figure out when we converge. Boom, we have to check our endpoint. Okay, let's try another one. Another one with the squared. We can do it. I'm going to start a new page. As you can tell, these take up a lot of space. Okay, x minus 3 to the 2n over n. Let's use our ratio test. So limit as n approaches infinity of x minus 3 to the 2 n plus 1 over n plus 1 times, this would be n over x minus 3 to the 2n. This is dividing by a to the n. This is the absolute value of this, has to be less than 1 for us to converge. Now let's simplify it. I'd have x minus 3 to the 2n plus 2 over x minus 3 to the 2n times n over n plus 1. That has to be less than 1. And again, I would have x minus 3 to the 2n times x minus 3 squared. This would cancel with this x minus 3 to the 2n. Over here, this, as we approach infinity, would trend to 1. So I end up with the absolute value of x minus 3 squared has to be less than 1. My interval of convergence appears to be 1, my radius of convergence. All right, so that means x minus 3 squared has to be between 1 and -1. So in this situation, I'm sorry, I know what to do. We know that x minus 3 squared is always going to be positive. We would not include this. We would just start at 0 and see what happens at 0, and then we'd go to 1. My fault for not doing that the first time. And then I could square root both sides, and it's not going to change things. Add 3 to both sides, and have x's between 3 and 4. Okay, so because x minus 3 squared can't be negative, we're just going to look between 3 and 4. Okay, now let's go ahead and check our endpoints for this guy. So if I plugged in x equals 3, we'd have 0 to the n, we would converge. Sum all your zeros up, you're good. Now if I try 4, I'd have 1 to the 2n over n. 1 to the 2n ends up just being 1 to the n squared, which is just 1 over n. We know this diverges because of because it's a harmonic series. So we would include 3, but not include 4. And this would be my interval of convergence. So in this situation, because we had that squared and the radius kind of gets jacked up, we wouldn't have a radius of convergence. The radius of convergence would actually be a half. The center would be 3.5, and we'd go out to 4 and down to 3. Okay, I'm going to do another one. I know these are taking a while, but they're good practice. Maybe you can just zoom forward. Let's do this one. Okay, we want to find the radius and the interval of convergence for this guy. All right, so limit as n approaches infinity of -1 to the, this would be n plus 2, n plus 1 plus 1. This is x minus 1 to the n plus 2, n plus 1 plus 1. Over, this would be 2, use parentheses, n plus 1 plus 1. Times, I'd have 2n plus 1 up there, I'd have the rest down here. Okay, let's simplify. I would have -1 to the n times -1 squared over -1 to the n times -1. That's important. This goes away. This goes away. This is just +1. I leave a -1, which won't matter at all. Over here, I have x minus 1 to the n times x minus 1 squared. That'll be over x minus 1 to the n times x minus 1. So this would cancel, and this would actually cancel, and this would turn into a 1. So I've covered this, I've covered that, that, and that. The last is the 2n plus 1. Over, this would be 2n plus 3. 2n plus 2 plus 1, which is 2n plus 3. Okay. So that has to be less than 1. We're finding the limit as n approaches infinity. I could pull out this -1, multiply, it becomes a +1. Divide by +1, nothing goes. This will trend towards 1, 2n over 2n, this is trending towards 1. So I end up just having x minus 1 to the first is less than 1. Here's my radius of convergence. And my interval of absolute convergence would be between 0 and 2. Now my interval for convergence, we would have to check 0 and 2 in my original equation. Series. So funny, I thought this was going to take less time to go through. Because when you do enough of them, it's just kind of quickly through it. But when you talk through them, it takes a while. So, check endpoints for conditional convergence, which is still converging. So x equals 0. I get sum, n starts at 0 to infinity, of -1 to the n plus 1 times -1 to the n plus 1 over 2n plus 1. This times this ends up being -1 to the n plus 1 squared. -1 to anything squared is just going to be 1. So we'd have a sum n starts at 0 going to infinity of just 1 over 2n plus 1. Does this converge or diverge? Well, I would have to actually use the limit comparison test. I'm going to have to compare this to 1 over n. If you look at the limit of this, you'd end up with a limit that's equal to 1/2, which is finite and positive. So since 1 over n diverges, this guy is going to diverge, which this means we diverge at x equals 0. Let's check x equals 2. If I plug in 2 for x, it becomes 1 to the n plus 1. That's just going to be 1 to the 2n plus 1. So this is just 1. This goes away. I end up with negative 1 to the n plus 1 over 2n plus 1. All of a sudden, I have an alternating series that's decreasing in terms that is going to converge. So we will converge at 2, and this would be our answer for our interval of overall convergence. Okay, I'd like to see the radius change a little bit, so let's go back and see if we can find another one where the radius changes. That one we did. We did that one. Did that one. If we go back to this one, I would say don't go to negative 3. I would go from 0 to 3. And then, what was that guy? We'd end up with 1, which would diverge. The other ones would converge. I could actually write this as a geometric series. This would be x minus 4 to the n squared. No, x minus 4 squared over 3 quantity to the n. This is a geometric series where x minus 4 squared over 3 has to just be less than 1, which is what we ended up doing. So there's going to be more examples on your quiz that are going to be done on your quiz. So make sure you do your quiz, and the problems really aren't that tough, but they are very involved. So just be prepared for them. Final question is this one. This is a good question. So the series below converges conditionally at 5. What can we say about the series at 2, 0, and 1? So if we converge conditionally at 5, this is a situation where the radius convergence would have to be 2. So we'd have a situation where, at 3, of course, we'd be convergent because we'd have a sum of a bunch of zeros. But we go up to 5 and we converge. Well, that means I would go down to 1, and I don't know if I would converge or not, but I do know that in between 3 and 5, I would converge for sure. So they ask you what's going on at x equals 2. You can say, well, I'm definitely going to converge because I'm in my radius of convergence. X equals 0. Well, I know that would actually be outside my radius of convergence, and I would diverge. X equals 1. This is a situation where we have an endpoint. I would not know. I do not know if we're going to converge conditionally, converge absolutely, or diverge. I don't know. So that's the situation for that problem. Okay? More examples and answers on your quiz. Make sure we do that, as well as there is some book work. However, the book problems are tougher than the problems that I did. So on the quiz, let's do those.